to have a talk here and in celebrating 15th anniversary of this Yau Center, and also birthday for the Professor Yau. So my title today is Mirror Symmetry, in particular from the viewpoint of moduli space of Calabi Yau threefold. And so I wrote here based on work of Hiromichi and Takagi. But actually, so this is directly related to collaboration with Takagi, but actually this, actually goes back to my old works when I was Professor Yau's postdoc. That means 92 to 93, and I worked with Professor Yau and means 92 to 93, and I worked with Professor Yau and classical one. So let me start from the definition, and here is the definition of Calabi Yau threefold. So smooth projective and trivial canonical bundle and some certain relation about some certain bunching property of this cohomology. And the property to describe mirror symmetry, so we focus the property of Calabi Yau. So we focus on the two structure of Calabi Yau threefold. So one structure is A structure, so-called, and the other structure is B structure. So A structure is rather easy to describe. So you know so as a polarization of Calabi Yau, we focus first the Kerak bond of Calabi Yau, something like that. And if we take a dual, then we have some cone structure, so-called numerically effective classes of algebraic one cycles, something like that. So naturally, we have cone structure like this. So B structure is something difficult to describe. So first thing we have to assume. So assume we have the family of Calabi Yau. And then, so if such a family we have, then we can we have the local system. So namely more explicitly Picard-Fuchs differential equations for the family of Calabi Yau. And sorry, so my talk is mostly focused on the threefold. So I did not write this. And then this is assumptions. And furthermore, so assume there appears some certain special boundary point. So sometimes you know that that's called large complex structure limit or actually important monodromy point in moduli space, something like that. And then there is a monodromy action. And then I will explain details. From that situation, we can construct cone structure, extract cone structure from there. That cone structure is often called monodromy nilpotent cone. And the mirror symmetry, so given Calabi Yau, so two structures we have, mirror symmetry exchanges basically two structures. So here is a little bit details. So this side is, I said, cone structure related to polarization. And so let me start from the B structure. Suppose we have a family as I described last slide. And then, so I'm suppose the certain boundary point, special boundary point, something like this. And then usually this boundary point, so, and usually this boundary point is not smooth, and we have to blow up to get the smooth boundary point. I mean the smooth coordinate. So here I describe the coordinate ring. So this picture, in this picture, I did sigma check. I mean the coordinate ring for the affine coordinate of the centered by the boundary point O here. And I'm saying that usually we will encounter this affine coordinate is singular. So what we have to do is the blow up suitable times, something like this. And then that's drawing a process we can describe in this way. So in dual language, and take a cone, a dual cone like this, and then so this drawing up process may be described by subdivision of this cone structure. And then subdividing this cone into sigma prime and introduces smaller cone. And I will describe regenerator R1 and R2 for this smooth cone. Okay, and then going back to the dual side, and each ray R1 and R2 correspond to the divisor we'll get after blowing up. R2 is divisor around here. And then for each ray or each divisor, we can talk about a monodromy around here. So that monodromy action I describe N1 like this. And then for this divisor, ray generator, or this divisor, boundary divisors, we can consider the monodromy action N2. And then they have to, if you look at examples, many examples, we can encounter the situation where the monodromy action, which naturally comes in this way, all monodromy actions N1 to NR. R is the dimension of the moduli space, and these natural monodromy actions are nilpotent. That's a situation where we can describe mirror symmetry. So if such an nilpotent action, actually in this context, pi1 is commutative. So because of that, these nilpotent actions are commuting linear actions. And then we can consider, because of nilpotent, we can take a logarithm of Ni and take a linear combination in terms of general parameter lambda I, and I denote this Ni. And this monodromy action naturally acts on the middle dimensional cohomology, H3. And because of nilpotent, we can consider this canonical form. So it's called monodromy weight filtration. Okay? On the dual side, going up, that's a structure, detailed structure, which we can extract from the B side. And the A side is we have Kera cone corresponding to this subdivision. We consider the subdivision of Kera cone. So Kera cone in general is very complicated object for the that's the main subject in algebraic geometry or Kera geometry to determine the shape of Kera cone. So in any case, after subdivision, we can make up the smooth cone, simplicial cone, and then I denote the primitive element kappa 1 and kappa 2. And again, corresponding to this construction, consider the general linear combination as a Kera, so inside the element of Kera cone, kappa, and general combination, and we can consider the nilpotent action, which naturally, which is part of the Hard-Lefschetz theorems. So this defines nilpotent action on the H even. Okay? That's a two structure, and basically the mirror symmetry exchanges this nilpotent action to this nilpotent action. That's a mirror symmetry. So based on that, so I defined, so here's my definition of the mirror symmetry. X is called the mirror of X check if there exists a family, as I described, where family and its complexification M bar, where we can find out the very special boundary point. And furthermore, as I said, two nilpotent actions which are related by linear action. So here is a more precise statement. Near the boundary points, two nilpotent actions are related by linear isomorphism, H even and H3, and by conjugation, something like this. And in particular, not only linear isomorphism, what is required, naturally required by in the context of mirror symmetry is that actually this linear isomorphism should come from the integral structure. One is the integral structure comes from H3, natural integral structure in integral cohomology element and cup product in cohomology. This gives us symplectic structure. On the even side, you know that there is a K group, numerical K group with symplectic structure. So by Riemann law, we have the symplectic structure. So this gives us, taking a Chern character, we can go up to the H even. But this is the integral structure for the left-hand side. So this linear isomer comes from this integral structure. And using this linear isomorphism, the two nilpotent actions are conjugated. That's under identifying parameters. So to define this Lifshitz action, the arbitrary number alpha I, and to define nilpotent action, arbitrary number lambda I are there. So formulating this equation that I identify, we identify two parameters. So in any case, so basically the mirror symmetry exchanges two nilpotent actions. One is from the A structure, the other comes from the B structure. With this integral structure. So that's a mirror symmetry. And that's mirror symmetry actually first appeared in 93. And so you know that the quantum cohomology, quantum product is related to Griffiths coupling with some additional data, so-called mirror map. And so something, our work 2018 is having this picture in mind, we can connect the two different things. One thing is so-called movable cone in birational geometry. So Kera cone is somehow generalized to so-called movable cone. And on the other hand, for this part, nilpotent action part, there is the notion of nilpotent cone. And these two notions are related to each other. That's my observation 2018. So anyway, this is very classical thing, but they still for me, a lot of work we should do. So today, what I'm going to do is one interesting example. So I mean, the definition may be easy, but proving mirror symmetry in general, as far as at least for me, it's proving mirror symmetry in general seems to be a very hard problem. So for me, the finding interesting example or typical example of mirror symmetry, that's my subject. So from now, I would like to focus on such a interesting example. So here is the example. Suppose we have the abelian surface, just abelian surface with polarization L, and the polarization is 1,8 types. And then with this ample line bundle, we can consider embedding. So to P7. So P7 comes from this polarization type. So in any case, by ample line bundle, we can consider embedding of abelian surface to suitable projective space. So in this case, you know that, of course, this is in terms of theta function associated to this abelian surface. And this kind of embedding problem has been studied by algebraic geometers. And here, this case has been studied in detail by Gross and Popescu near 2000. And so the result is the problem around here is how the image of this embedding. So namely, how the vanishing idea of the image of this embedding And their result is as follows. So certain nice form of ideal plus a little bit complicated part of given by the 3 by 3 minus determinantial ideal. So in any case, this is their result. And then, so somehow they just focus on this quadratic, four-quadratic case. So usually you know that the theta function satisfies quadratic relations. And this four equation comes from such relations. And to describe the image, we need additional generator. That's their result. But for us, what is interesting is to simply look at this quadratic equation. So namely, so four quadratic equations inside of P7, that already indicates a Calabi Yau threefold, right? And so, but this four quadratic is very special type. Omega 0, omega 1, and omega 3. This is the parameter, and the others are coordinate, homogeneous coordinate of P7. Now, here is the result. So if forget that 3 by 3 minor part, so just focus on this quadratic part, four quadratic, and the vanishing of four quadratic inside P7, and then we'll got the singular Calabi Yau complete intersection. So how the result? So here is the detailed description, and this vanishing locus, on that, we have naturally Heisenberg group. So Heisenberg group naturally comes from because we have a theta function for the embedding problem. That's Heisenberg group. The reason we will have Heisenberg groups here. And also another point is that we remove the, oops, sorry. We removed this part. So if we include, if this part is here, that for the vanishing locus, then we simply recover the abelian surface, but we forgot that part. So because of that, we will have the pencil of abelian surfaces, and actually 64 base points. Where we have 64 ODP, ordinary double point. And so that's a structure more or somehow tells us the structure of Calabi Yau threefold. So one parameter family of abelian surfaces. That's the structure of this vanishing locus, rough structure of this vanishing locus. And then so this singularity base point are 64, and the singularity type of ODP, and then we can consider small resolution. So here I described a little bit schematically one of the ODP from the 64, and the P1 is, this is familiar picture, but slightly different. So P1 is parameter, pencil of P1, and here ODP, and the first thing is blow up along these abelian surfaces, abelian surface, and then we'll have exceptional curve here, and then take a flop, and so pencil of P1 and the exceptional curve P1 becomes parallel, and then this gives us abelian fibrillation over P1. That's so in any case, that from the special family of four quadratic, we will have the abelian fibrillation. And so the point is that these two are Calabi Yau, smooth Calabi Yau, and these two are this free Heisenberg group action. That's the point. Then here is the Hodge numbers. So we started from singular complete intersection, and then here's a Hodge number. The before resolution, we have only one Picard number, generators of Picard group, and after resolution, so fiber class becomes originally baby divisors, fiber class become Cartier, and then because of that, so we have rho equal 2. And if you look at the fiber is abelian surface, so Euler number 0. So because of that, Hodge diamond is something like this. So very simple Hodge diamond. So it was try to look into the details. So actually, because of that, so Gross Pavanelli, so they looked at this Calabi Yau a little bit closely, and then they came to the conjecture. So X is abelian fibered Calabi Yau, and then mirror dual, how's a mirror? So they come to analyzing so-called Brouwer group or those kind of things. They come to this conjecture. So abelian fibered Calabi Yau, and the mirror dual is free quotient by Z8. And then mirror, how about the mirror of this one is actually mirror, it should be Z8 cross Z8. That's they came to the somehow as a conjecture. And then so something supporting evidence for this conjecture was these two are, this has vibration by abelian surface, and this Calabi Yau is dual vibration, fiber-wise William chi. So because of that, these two are derived equivalent. That's a pretty nice picture supporting this mirror symmetry conjecture. Now I will come to the, I'm running short time, so very quickly. So my focus is how about the mirror symmetry? So I defined how the mirror symmetry and from the viewpoint of family of Calabi Yau. So what I'm doing is the construct family of Calabi Yau. 3 types of Calabi Yau appeared here. So starting from this idea generated by 4 quadratic like this, and then naturally over P2 omega. Omega is the parameter space, and the X is total space. Here is the total space of this family. And similar thing, and Z8 and Z8 cross Z8, this comes from the Heisenberg group action, free actions. So because of that, we naturally have the similar family for these quotients. And it's quite often, if you have experience making family of Calabi Yau, you can recognize this kind of things. So namely, maybe here. So if we, for example, mirror quintic, we usually start from the P1 parameterized by psi and consider this mirror family. But if we construct such a family, then we recognize natural group actions, and we have to take this quotient to get a nice family to have mirror symmetry. And the same thing happens here. And actually, this idea has a little bit larger symmetry. I did not here. Heisenberg group contained a little bit larger symmetry group of this idea, and this larger group acts on this total space. That's a situation, and correspond to Z5. And here is the result. So we have to take suitable quotient by using this larger symmetry group. And the larger symmetry group, taking larger symmetry group is not the right one. So it turns out a little bit smaller, small group, subgroup we have to consider. So I don't justify the choice of this small group, but this is the result. So any case, so starting from this 2 quotient and then entire total family, we can take this. If we take this small subgroup and take a quotient, and then we will end up this family and this family over certain toric varieties. This side is general fiber is X over Z8. This side is Z8 cross Z8. And 2 families we have in this way. And then our claim is that these two describe mirror symmetry very nicely. So I skipped all the details, but how it's nice. So here is a description, and this, as I say, just please remember, just remember this family and this family over same parameter space, or but same toric variety. And then I'm describing this toric variety. This toric variety symbolically by Politov I described. And if I added a certain discriminant of that family, both two families I constructed, two families comes from the four quadric, so discriminant locus is the same. Only the difference is by the quotients.
Time is up, sorry.
Time's out? Yeah, so I'm sorry, few minutes. So I finished. So blowing up this locus suitable time, and then we will end up the boundary point, which actually correspond to the A and A prime, B prime, C and C prime, and this A, B, C correspond to A and B and C, and A prime, B prime, and C prime is the birational model. Birational model I showed. So here is the another. So for this boundary point, we can apply. We can verify the mirror symmetry as I described. Now here is a ground-fit invariant coming from the boundary point, or somehow the modular property, cross-site modular form appears. We can observe. Okay, so thank you very much, and sorry.
Thank you. So is there any question or comments? So may I ask you a question, Professor? So how about the higher dimensional Calabi Yau? Is the mirror symmetry, is there any essential difference? Higher dimensional Calabi Yau?
Basically, I think basically idea seems to be the same, similar ideas should work, but I'm not so sure about the details.
Okay, thank you. Okay. So our the last talk of this afternoon is by